Hi, I'm Tom Joy and I'm here to present our work Sample Dependent Temperature Scaling for Improved Calibration. Neural classifiers are known to be miscalibrated, where they are typically overconfident. What we mean by miscalibrated is that their accuracy does not match their confidence. To address this, we present adaptive temperature scaling, which predicts a temperature value for each individual sample. This leads to better calibrated models when compared to vanilla temperature scaling. The method is fast to train and test, requires very little computational overhead, and is easy to implement. Adaptive temperature scaling can be applied to any pre-trained classifier which predicts a softmax distribution as its output. Not all samples in the wild are equal, with different samples contributing different amount to the expected calibration error. Some are what we call overconfident, in that they contribute a positive amount. Some are underconfident, in which they contribute a negative amount. Consequently then, it is inappropriate to scale all the confidence values by the same value like you would do in vanilla temperature scaling. Here, in adaptive temperature scaling, we respect this and predict a temperature on a per sample basis. To do this, we use the latent space of a VE as a representation of uncertainty. This is empirically motivated and we will discuss this shortly. The temperature is then predicted from this representation using a multi-layer perceptron. You can see an outline of our model in figure 2. In the red you can see a pre-trained classifier which is typically consists of a feature extractor and a final linear layer. The VAE is then learnt off the features of the neural network to get a latent space Z, from which we then predict a temperature via a multi-layer perceptron. So why do we use a VAE? Latent spaces of a VAE separate out the samples which tend to contribute heavily to ECE. We can see this in figure 3, where the calibrated samples, in pink, tend to be clustered around the centre of a single Gaussian. Miscalibrated samples which contribute either positively or negatively tend to be placed around the outside of the cluster, as you can see in orange and yellow. Furthermore, incorrect predictions which contribute heavily to the ECE are placed by black crosses far away from the cluster. Consequently then, we empirically motivate the VAE as a suitable input to predict the temperature value. To train our model, we train using a validation set, where we now only optimize the VAE and the MLP using the cross-entropy loss. We can see an example of how we can see the algorithm, roughly in algorithm 1, where first we take a random batch, compute the VAE gradient using the standard elbow. We then construct the MLP input, which consists of the latent probabilities. We then maximize or optimize the cross-entropy loss by only optimizing the temperature, which is the output g theta. We then update the parameters using gradient descent. It is worth noting that training is very fast due to the use of the classifier features. So here you can see in the results that generally calibrate that in all situations adaptive temperature scaling outperforms vanilla temperature scaling. We tested this on two networks, wide ResNet and ResNet 50, on the two datasets CFAR10 and CFAR100. We also have additional results for Tiny ImageNet in the paper. We tested our model on multiple objectives, so you have training using a standard cross-entropy loss, the Breyer loss, and then deep ensembles. Furthermore, we also observed that our model performs well under dataset shift, where we test against the popular CFAR10 and CFAR100 corrupted calibration experiments. Here is an example of the reliability plots left for temperature scaling and for adaptive temperature scaling right. You can see that generally adaptive temperature scaling obtains much better calibrated values than vanilla temperature scaling. Thank you.